All right, everyone, welcome to office hours. Per the usual, we're going to wait about 5 minutes for latecomers to roll on in. We've got a fantastic crop of questions today, and I'm really looking forward to office hours, so talk to you soon. All right, everyone, welcome to CS6476 office hours. This is just a brief reminder that these office hours are recorded, and if you choose to participate via text or video chat, your participation will be recorded as well and later posted to the class for those who couldn't make it to view. These office hours start with about 40 minutes of answering questions that were pre-posted to Piazza, and then we'll have 20 minutes of open discussion time. This week's questions were really great and covered a pretty broad spectrum of the particle filtering assignment, from part 2 of the homework, where particle filters start, all the way to part 5, and I'll even talk a little bit about part 6. So we've got a lot of material to cover, and I'm looking forward to getting into it. The specific questions I'm going to be addressing today are, first, what's the difference between tracking and detecting? And I think this is a very fundamental question, so I'm going to spend a bit of time on it to try and really hammer home the difference. And hopefully, if I do my job well, I'll convince you that there is a fundamental difference between tracking and just detecting. Then I'm going to talk a little bit about part 3 of the problem set, which is the appearance particle filter, and particularly how we compute the template update step and what exactly best of T is. I'll follow that up with a fairly lengthy discussion of occlusion. If you post the first question on my office hours thread, I think about it the most, so you get more slides. And finally, I'll spend just a little bit of time about tracking multiple objects. I think you'll understand when we get there why I'm not spending more time on that. All right, so here's the agenda. I'm going to start by giving some unsolicited advice about the problem set, mainly because I see what I think are a large number of people struggling or stumbling on Piazza, and I'd like to sort of gently nudge back in what I see as the correct direction and approach to this problem set. Then we'll go through the various questions that were asked, and finally end with about 20 minutes of open questions where it can be anything computer vision related. I'll try and stop after each section and pause for questions. You should also feel free to ask questions during the presentation, although I might not address those until I pause. So let's start with some friendly but ultimately unsolicited advice. No one asked me about the general approach, but I'd like to say that this problem set is a weird one, because what trips people up are these very subtle implementation errors. And it's possible to have your code look like it's working, but contain small errors that really poison the rest of the parameters tuning experience. I am seeing many people on the class forum who have started investigating some fairly sophisticated methods to answer some of the parts of the problem set that aren't the challenge problem. And this really shouldn't be necessary. I have a solution that works for all parts of the problem set that doesn't involve any special techniques beyond what's described in the problem set description. So you're welcome to implement more advanced techniques, but they certainly aren't necessary for success on this problem set. What's really going to help you as you work are, one, paying very careful attention to correct implementation, checking your assumptions. I really like to visualize every frame of my particle filter and print out information about a small number of particles so I can confirm the filter's updating in the way I think it should. I also recommend paying careful attention to the motion models and what the parameters you're setting mean, because often the solution to a subpart of the problem set is having a well-tuned motion model rather than adding extra bells and whistles into your code. And hopefully what I mean by some of this will become clearer throughout office hours. But let's take a big step back and say, what are we doing here? And how is this filtering or tracking different from just detecting an object, say, using match template? Some students have noticed on Piazza that match template is called within the Kalman filter driver code to provide a measurement. And we're wondering, why do we have all this filtering or tracking fluff wrapped around it? Why not just use the output of match template as the location of your object? And the core difference between just doing detection and tracking is that with tracking, we incorporate additional information. We typically have a motion model, which tells us how we think the object behaves, how its state evolves with time, or put less formally, how it moves. And we have a sensing model, which tells us how much we trust our measurements, and in particular, how much we trust our measurements relative to our motion model. So I've put sort of this core idea in words, but it comes down to this equation from the problem set, which I believe is also shown in lecture, where a belief in the state of the particle, so x of t is not just an x coordinate, it's an entire state vector, is proportional to the probability of getting the most recent measurement we got given our estimate of the state, or given the state at time t, multiplied by the probability of getting the state x of t given our prior state and the known motion. So that's our motion model mentioned here. And this was our sensing model mentioned here. And finally, we also maintain a prior belief, which lets us sort of aggregate many, many measurements and pool them together. And what we can do with tracking that we can't do with basic detection, sort of template matching, is we can solve problems where there are multiple objects, we can solve problems where there are occlusions, and we can solve problems where the measurements are very, very noisy. And I'd like to show you some examples to hopefully convince you that this is true. Don't believe me, believe the examples. So in my first example, I've got 3 red circles that are going to move around the page. And I want to track one of them. I'll consider it a wrong answer if we track this circle or this circle. I want to track this circle as it moves slowly around this image, and the image has got some wonky background with blue and green squares. To help out the process, I'm providing a template, which is just a cutout around this circle. So this is a very, very similar problem to some of the early bits of your problem set. And we're going to apply both a simple detecting technique and a particle filter to this problem. So let's see if this works. I've been fighting with video in LibreOffice all day. But our goal is to track this particle in the upper left. And we're going to use on the left here a particle filter whose motion model is just the position of the particle, or the position of any given particle moves a little bit during the motion update step. That's what this adding noise does for you. And you can think of this intuitively as requiring that the red circle not move too far. This is a mathematical encoding of the idea that all circles move slowly. And then on the right, I'm going to show detection only. So I'm running template matching and picking the best, largest, or best matching point in the image. All right. So here we've got the circles moving, and it's a bit chaotic, but on the left, the particle filter, it's nicely tracking the one circle we started on. It's made almost a full revolution. Whereas on the right, in the template matching detection only, where we don't have any prior belief about state, and we don't have any motion model, you see the detection jumps around based mainly on either which circle is on the blue background, which the template includes a little bit of, and some of NumPy's rules for determining the maximum if two objects are equally good. So given my criteria that I wanted to track only the circle that started in the upper left corner, it's clear that we're able to do so with the particle filter, and we're unable to do so with detection alone. The other circles throw off our matching process. All right, I'm going to let these run for however much longer they do. OK, now we're done. We're back to our original state. So that's one example of doing something with filtering or tracking that you can't do with pure detection or pure template matching. The second example, and I like this one because it ties nicely into something we'll talk about a little later tonight, is dealing with occlusion. So here we want to track the position of the red circle, and we have the foreknowledge that it moves with constant velocity. So I've set up this little contrived example where we have the red circle, and I'm just going to show you its motion before we put tracking on it. And so you saw here the red circle passed behind the blue barrier and disappears completely from the image for a while. you and I are smart. We have some intuition that it's just hiding and it's going to reemerge. And hopefully we can see that with the particle filter, we'll see something very similar. So again, I've got this sort of dueling setup. Left is particle filter, right is template matching only. Here I'm using a more complicated motion model, but my motion model is just encoding the idea that the velocity is constant. And all I'm doing is the velocity remains mostly unchanged with a small noise term. A little bit of noise always helps your particle filters be more smooth. And we update the positions with those velocity terms. So we went from having a 2D state to a 4D state in our particle filter. And if we run this, so there's an initial convergence as the particles cluster. And now look, template matching has lost the circle and now has it again. But the particle filter maintained constantly its estimate of the position very, very nicely. And I'm actually going to run through that again because I think it's fun and it's hard to watch both at once. So particle filter maintains position estimate, template matching guesses upper left corner. So this is really the power of filtering. It lets you deal with very noisy measurements. It lets you deal with measurements that are occluded or missing. And it lets you deal with tracking only one object when there are many similar objects in your scene. So at this point, I've said what I want to say about tracking versus detection. And I'm going to answer a few questions about that topic before we move on to the appearance particle filter. So the first question I see is, for multiple particles you showed, should we have separate template coordinates to start with? It will be 3 different tracking algorithms for particle filter. I think what's being asked is that for this example, where we have 3 circles, showing, do we need to have 3 particle filters? If you wanted to track all 3 circles, then yes, you'd want to have 3 different particle filters. I set up this problem saying I only want to track the circle that starts in the upper left-hand corner, so I needed only 1 particle filter. And I had to be a little careful about initialization to make sure my particles ended up on that circle and not one of the other 3. The easy way to ensure that happens is the template has little bits of blue here in the corners, which means my initial particles are going to congregate on the circle in the blue quadrant. And then because we have this assumption of slowness and we aren't letting the particles disperse very far, they always stick with this circle and never find any of the other 2. We also have a question, which is, we do not have any test cases with multiple objects with the same appearance, right? Sort of. You certainly don't have any test cases like these I'm showing, where there are 3 objects with an identical appearance and you don't want to find 2, you want to stick with your original. Many of the videos with pedestrians have a lot of pedestrians. And in my experience, when I solved this p-set, one pedestrian looks an awful lot like another. And sometimes you'll find your particles find one they like better than your original pedestrian if there's been some changing in the scene and some motion and it doesn't look exactly like your original template. So where you don't have to deal with this extreme case where you have 3 objects exactly the same, you'll certainly later in the p-set have to deal with problems where you have objects that look similar. All right, seeing no further questions on tracking versus detection, I'm going to jump to the appearance particle filter. So this is now thinking a bit about part 3 of the problem set. And part 3 of the problem set is a small tweak to the particle filter algorithm. It's a tweak based on the idea that if the object we're tracking is changing, we'd like our algorithm to accommodate that and not at some point lose it because it's changed so much it's no longer recognizable. And if the changes are slow enough, we can do this by just updating our template based on the most recent measurements. And so the way we do this is encoded in this equation, which we've gotten lots of questions about. Your template at time t is alpha times this funny best of t plus 1 minus alpha times your prior template. And alpha here is a parameter that's going to be less than 1. which is controlling how quickly the template changes. So if alpha is very close to 1, you'll almost always use only best of t as your next template. Whereas alpha is very close to 0, you're only mapping in a little bit of best of t, and you're taking template of t minus 1 to be most of your new template. So you have to set alpha in this case to match the rate at which the object you're tracking is changing. Mitt Romney's hand, when he moves it, changes very fast, which means you might need a larger value of alpha. The weird morphing eclipse that's used by the autograder changes relatively slowly, which is why the autograder 0.5 alpha is appropriate. And you'll want to experiment with this parameter for the different videos you have, using the intuition that large values of alpha are for templates that change quickly, and small values of alpha are for templates that change slowly. So I've been dodging the question here. What exactly is best of t? How do we get this, this magical secret sauce that's going to make our template better at time t than it was at time t minus 1? And in words, best of t is just our best guess at what the template should be at time t. So we're going to take the frame we just got, and we're going to use all the information our particle filter has accumulated and learned, and we're going to pick a patch of the image to represent our best guess at what the template should look like. I find those words, frankly, difficult to follow when I'm saying them. I much prefer this example I've got on the next slide, which I built out of one of the tracking Mitt Romney's hands frames. So here we've got a frame from the video. It's just been processed. The particles are clustered nicely on Mitt Romney's hand. And here I'm using a square template that's right now centered on his hand. This frame was processed using template at t minus 1, which I'm showing here in the lower right. So we multiply that by 1 minus alpha, and we pull right out of this video frame our best estimate of what Mitt Romney's hand looks like now. And we multiply the new template, which we're calling best of t, by alpha, and we merge those together, and we get an updated template that we'll use to process the next frame. I found this particular frame and pair of templates interesting because at this point there is some glare on Mitt Romney's hand that creates a little bright line here you can see. So you actually can see the template changing, not dramatically, but you can see that appears in the template where it wasn't present in the template at t minus 1. And I'm not going to tell you what value of alpha I used here because that's probably giving away too much information about the problem set. But this is the general template update process. There's one subtlety, which is how exactly do we select this window that we're going to pull from the frame? And there are two approaches. One is you can take the weighted average of all your particles, which is this nice red square or red rectangle you're rendering, and pull that as your template estimate. Or you can find the very best particle, which is the one that best matches the old template, and use that to create your new template update, or your best of t. I'd be a bad TA if I told you all the answers, so I recommend you try both of those approaches, see what works, see if there's any difference. And that's what I have about the appearance-based particle filter. When I was implementing it, I definitely was thinking of this image and thinking of this equation sort of as pull a frame out of the current frame, blend it in with the old template using alpha to determine how quickly things are changing. So we've got two questions that rolled in while I was talking. The first is, can we add alpha as an additional dimension to our particles? Off the top of my head, I wouldn't recommend it. I don't think it's a standard practice, and I haven't thought about it enough to know if it's going to lead you way astray. You certainly don't need to add alpha as a dimension for this problem set. it would be a little bit of a strange thing to do. We typically think about dimensions as physical properties of the object. If you do finish the problem set and are looking for more fun particle filter work to do, I'd be curious to hear if anyone did try that, what it looked like, but I wouldn't recommend it as a first-line approach. We also had a question going back to the prior section, which was, in the 3 red circle example, template matching might catch the wrong circle during running particle filter on some frame. How to neglect this wrong matching? I'm going to pop back to that example. That's really the beauty of the particle filter is, let's say that at one instant we found the wrong circle. If we've set up our motion model and sensing model right, we know that there's an ambiguity, and we know that we shouldn't necessarily believe one spurious sensor reading. I'm being very anthropomorphizing here. It's all just particles and numbers. But hopefully you've got enough particles sticking with the right circle because your motion model works well, that the probability of you jumping to that other circle is low. And it's all probabilistic in the end. This is one of the things many people hate about particle filters, is there's always a chance they just do something wild and wrong. It's just a vanishingly small chance, which is good since we use them in everything. All right, so the next question we had was about how to handle occlusions. In particular, I've seen some anger directed towards the man who walks in front of the pedestrians in the crosswalk and steals people's particles. How do we deal with that? And I wanted to reflect that question back to all of you and take maybe 20 seconds to pause and ask, at the basic level, without getting into all the implementation details, why do we expect tracking either with a particle filter or a Kalman filter to handle occlusions? I mean, you don't need to answer in text or anything like that, but just think about it for a moment and then I'll show the answer I would give. Okay, this is how I would answer this question. And there are many answers that are mostly equivalent. And my answer would be, the filter maintains a belief about the system's state that sees you through the bad times. And so even though you're getting measurements that are utter garbage because there's a man standing in front of the pedestrian you really want to track, your motion model and your prior belief are good enough to see you through. And that's really the key to part 4 of this problem set, is that if you have a motion model which is going to be reliable during occlusion, there's nothing in the occlusion that breaks your motion model. If your motion model is very good and you have a solid prior belief before the occlusion occurs, that can see you through some amount of time getting these very unreliable measurements during the occlusion. And hopefully this makes some intuitive sense. We've already shown one example where the circle essentially disappeared for a while, but because we had a good motion model, the state just propagated right across the blue barrier, and we were able to pick the circle right back up on the other side. It really, really comes down to the quality of the motion model. And I'm going to show an example that I hope will convince you all that this is an approach that with a good motion model, you can get good results on this problem. And I'm also going to show you what a bad motion model looks like. So again, I'm going to be showing 2 videos at once. These are both videos of part 4 on the problem set. If any of these videos show up in someone's report, we'll all be very disappointed and we will not think you're clever. So make your own videos, don't steal the ones from office hours. The video on the left is an example where we have a good motion model that maintains its state during the occlusion. And the one on the right is a bad motion model that's going to lose its good estimate of state during the occlusion. So let's see if I can run these. All right, occlusion and lost state and maintained state on the left. So these videos are going to be posted. If you want to go back and run that again and again to look at it, you're welcome to. But the idea is, on the left, we have a motion model that is well-tuned enough that it's going to maintain its state during occlusion. And I've added this note at the bottom because many people are trying to be very fancy in their handling of occlusion and build in advanced techniques. The focus here in part 4 is just incorporating an extra dimension, the scale dimension, into your problem set and tuning a motion model well enough to handle occlusions. You don't have to be fancy unless you want to be. I also want to note that because we're subclassing the appearance particle filter for the MD particle filter, there's a chance you can shoot yourself in the foot with template updates. And so I didn't mention it before, but in the upper right of both videos, I'm showing the template I'm tracking. And if you let the changes of appearance accumulate too rapidly, it can be hard for these multidimensional particle filters to grab state. So I'm just showing another example of good behavior on the left, bad behavior on the right, and let's quickly run that. So in both cases, I'm updating my template slowly. But in the case on the right, or in both cases, I'm updating my template. In the case on the right, I'm updating it slowly, roughly corresponding to how much the woman's appearance changes. On the right, I'm updating it way too fast. And if you go back and rewatch through this video, you'll see during the frames where there's an occlusion, the template essentially changes to be exactly the occluding pedestrian. So this is a risk, and you really don't want to be doing fast appearance updates unless you absolutely need to. There's a typo in this slide, too many appearances. So what if you absolutely need to? Part 6 of the problem set. Or at least it might be very helpful to you if you could update an appearance model while also tracking changes in scale. The first thing I'd like to say is it may be somewhat difficult. There's a fine balance with the appearance-based particle filter of changing too fast and losing what you're tracking, or changing too slowly and losing what you're tracking. There's an advanced technique you can try, which is only updating the template if some error metric you choose is less than a threshold. And two obvious candidates are the standard deviation of the particles. So if the particles are very dispersed, you're uncertain where the object is and might not want to update your template because you're worried about getting it wrong. Or you could directly check, has there been an enormous change in the template? Is template minus new template large or small? And you have to do some squaring and other operations there. But those are some ways you can try and deal with the need to have fast appearance updates and possibly occlusions. So that's what I have to say about handling occlusions. And I saw at least one question come in. So it was asked how to incorporate a scale factor into a model. So I'm going to pop way up in my presentation to here. Your motion model can have any state variables you want in it. In particular, here I have 4 dimensions. I have 2 positions, x, y, and 2 velocities, vx and vy. And my motion model updates all of them. Similarly, my sensor model could take into account any operation on these state variables. So you can incorporate a scale factor into your model. You're adding an additional column to your states. So instead of having an x and a y state, you now have an x and a y and a scale state. You also then, when you're doing your sensing, have to take into account the scale factor. And I believe it's recommended in the problem set to take a look at CV2 resize. So you size the template appropriately for the measurement you're making based on the scale factor. And you have to decide how your motion model is going to incorporate scale. There are a number of different motion models you can use that are going to that are going to, sorry, I lost my train of thought here. There are a number of motion models you can use that will get you good results with scale. You have to play with it and try the right one. A bunch of questions rolled in. I'm not sure the order, so I'm just going to pick one and answer them. One question is, can I explain how a good motion model helps handle occlusion? Yeah, absolutely. And let me go to this example. So what you're going to see is, in the good motion model case, the occlusion passes, but my particles aren't moving wildly and I don't lose track of the object. In the bad motion model, there's enough motion of the particles that by the time the occlusion is passed, I no longer have an accurate read on the object. Let me see if I can run that video again. So good motion model, the occlusion passes and my particles don't diverge. Bad motion model, the occlusion passed, my particles diverged too much and I lost the object. This isn't the only difference between the left and the right video is the tuning and parameters of the motion model. I'm not doing anything fancy in the left video that isn't done also in the right video. It's merely a matter of the motion model. And what you want in a motion model, if you're going to have an occlusion, is that it propagates the state forward very accurately and doesn't introduce too much dispersion. So you want to have an accurate estimate going into the occlusion, and you want to be able to propagate your state forward very accurately. Let's go through the movie once more, just because it's hard to watch both at once. So note that the particles on the left maintain their position on the woman's back, and that's entirely due to the motion model we're using in this left video compared to the motion model in the right video. Okay. The next question was, how to identify occlusion happened based on the motion model? I generally wouldn't necessarily try to identify if an occlusion is happening. I would try and identify, is now a good time to update my template? And really, it's picking an error metric and only updating your template when that error metric is small, at least at the most basic level. And there's a ton of research into the topic of occlusions. One of the fun parts about taking a graduate class is you get to sort of skim up against the state of the art occasionally. But really, I wouldn't try and detect an occlusion using the motion model. I would try and make my motion model robust such that occlusions aren't a problem and I don't have to detect them. I maintain my state and propagate it forward despite the bad measurements and can pick things back up when the occlusion ends. All right, the next question was, Scott says, it was found that the autograder fails if it's a particle variable that isn't 2D, so adding a scale factor seems to break it if you add it to the particle filter class. Gosh, I really can't comment on that without opening the autograder code and poking around a little to see what they were going for. You can always add your additional dimensions either as additional member variables or to the MD particle filter class if need be. But adding a scale dimension is definitely the intent in problem 4 and building a good motion model for it. The last question I see is the good model or bad model related to velocity? I think I'm going to leave that for all of you to experiment with and figure out. When I did this problem set, I think I tried 6 or 7 different motion models for handling this occlusion problem, and it was a really great learning experience for me, so I'm not going to take that away from all of you. All right, so that's all I have about occlusions. We're burning through time quite quick, so I'm just going to talk briefly about tracking multiple objects. And it's quite brief because I only have one key point or key question, which is object motion coupled between the objects in a predictable way? For example, do you know that if object 1 moves left, object 2 is also going to move left? And an example of coupled motion is when you're tracking astronomical objects like planets or comets, and you have them in close proximity where gravitational effects matter and are significant, you have to take into account in your motion model for each the position of the others. So that's an example of coupled motion. In uncoupled motion, if you have a bunch of mice running around randomly in a cage, that's uncoupled motion. It's also uncoupled motion if you aren't able to have a predictable model that says how these objects should move together. So I have two different recommendations depending on if the motion is coupled or uncoupled. If the motion is coupled, then you need to use one particle filter whose state variables include the state variables for each. There's a typo in this and it's bad enough. I'm going to fix it immediately. That shouldn't read particle. That should read object. All right, back to the regular scheduled programming. So if the motion is coupled, you have to use one filter whose state has variables related to each of the objects. That's important because in your motion model, you need to use all of those state variables to calculate the coupled motion. If the motion is uncoupled, meaning you have a model where the motion doesn't depend on the other objects, then just use n filters. One of the reasons we ask you to implement these as objects is it's very easy to instantiate n objects and just have all of those filters running independently. And I don't make this recommendation lightly. I make it because this is mathematically equivalent to using one filter whose state has all these variables and an uncoupled motion model. Gosh, this slide is a bit of a mess. I left out the last bit of that sentence, but it's mathematically equivalent to having one filter whose state has variables for each object with an uncoupled motion model. So just use n filters. It's much cleaner and it's good object-oriented programming practice. All right, we now enter the part of our program for any type of question related to the prior slides or related to the problem set in general or just related to the topic of computer vision. So a question has been asked. This might be very obvious, but would it be possible to give the steps in order in a simple description of what needs to be completed for particle filter, appearance particle filter, and MD tracking, particularly what happens in the process part of the coding assignment for each of those sections? So I don't want to give too much detail here because a big bulk of the assignment is figuring out how to implement this particle filter in code and what to put in each section of the code. In my prior office hours, I showed sort of the particle filtering cycle that involved getting a new measurement in, moving particles or updating their state, calculating weights for your particles based on the measurement, and then resampling your particles. And that really is the heart of the particle filter. I advise looking back at that for implementation details. The next question is, I'm not sure how to change the representation of particles for part 4, incorporating scale, which still allows reuse of appearance model particle filter. Can I make a new variable for the particle scale? So I don't want to get too into the weeds of implementation details, in part because it's very hard if you're not sitting at an IDE to write code and hard to do verbally. I will say that it is the right thing to do to incorporate scale, even if that means you have to break some of the object-oriented reuse principles. All right, I see a bunch of questions rolling in. So one is, can I give an example of a motion model for sample motion, i.e., I know it's moving to the right? Yeah, let me think for a moment. So generally you don't have such great knowledge that you know something's moving to the right. That's a sign you're probably overfitting to a homework problem rather than dealing with a real world scenario. But let's say we have a particle or an object that's moving only to the right. My motion model for that case is going to be a velocity-based model. I'm going to assume I don't know how fast the particle is moving to the right. So for my state variables, I'm going to have the x position of the object, the y position of the object, and since I know it's only moving to the right, I'm just going to have a velocity on the x, so a vx. And my motion update law is going to be x goes to x plus vx. And I always like to add a little noise, so we'll say 1 pixel. I haven't seen the video of this always moving to the right object, so I don't know for sure. Y is just going to go to y plus a little noise, since we don't have any motion in the vertical direction. And vx is going to go to vx plus a little bit of noise. And I've tried to scroll that here on a piece of paper, and we'll see if the webcam can focus on it. Yeah, so you have x going to x plus vx plus some noise, y going to y plus some noise, and vx going to vx plus a little bit of noise. So that's how I build a simple motion model for something that I knew was moving to the right. I don't know how fast it's going, so the particle filter is going to find v based on its initial distribution, and the noise will help it refine its estimate over time. Okay, there was a question, are we allowed to add more classes in ps5.py and use them from experiment.py? I'm going to ask you to ask that on Piazza. I'd prefer not to make statements about what we are or not allowed to do here during office hours, just because it can get confusing and isn't super fair to the students who don't attend. Okay, the next question I got is the 3 guys' motion are coupled, so we need a state with 4 times 3 equals 12 parameters. I'd like to reflect that question back to you and ask, why do you claim their motion is coupled? And if it is it coupled in a way that's predictable that you can write it down as a mathematical equation? And will people ponder that? I'm going to skip to the next question, which is scale correlated with position x, y? It could be in your motion model. I'm going to be a little vague here, but you can certainly build a motion model where scale changes with x or y position, but you could also build a motion model where scale changes in the same way that x and y have been changing. Namely, you know it's about what it was in the prior frame and it's not changing too much. There are a lot of options, and experimenting with motion models is really one of the interesting parts of this problem set. All right, additional questions? We've still got 12 minutes. We got through the slides much more quickly than I had expected. Scott asks, so what's on the final? Can't really talk about that in office hours. I recommend not skipping any of the lectures and keeping current because it's important material. All right, seeing no additional questions, I think we'll call it 10 minutes early tonight. Thank you everyone for attending. I always appreciate the audience that shows up for these, and I really, really appreciate the good questions that give me something interesting to think about on Oh, 2 questions. See, the trick to getting questions is to pretend I'm going to end office hours. All right. So the first question I saw, it was, is adding additional columns to the particle array that is not really the state, but just something I would like to resample along with the particles a good practice? I don't know. It's an implementation detail that I don't have a strong opinion on. I think if I were doing it personally, I'd like to keep my state in one place and just have a separate column variable somewhere else to incorporate some other variable. There are ways to do resampling where instead of getting the new values, you get an index to the new values, and you want to apply those to whichever arrays you want. The other question I just saw come in was, can I explain the belief equation? And yes, I'd be happy to talk about it a little. But first, I'm going to pull that slide up again so I have something to talk about. Okay, so this is the belief equation. On the left-hand side is our belief about the state x of t. So how strongly we believe x of t is the true state. Remember here, x of t is a vector that incorporates all of our state variables. So it could be the position, or it could be the position of and velocity. But our belief of x of t is how much we trust this state, or how likely we think it is to be the true state. And so we're saying that's proportional to. And proportional to here really just means we're missing a scale factor. So we can't put exact equality, but we're saying as these values change, the belief of the current state changes. So on the right-hand side of the equation, we've got 3 parts. We've got a sensing model, we've got a motion model, and we've got our prior belief. So our prior belief, x of t minus 1, is probably the easiest one to understand, so we'll start with that. And this is just how likely we believe the state was at time t minus 1. So if we're doing a particle filter, how likely did we think the particle or the state was at time t minus 1? Then we have a motion model, and this is how likely do we think the state xt is given any known motion. So this would be adding in the velocity factors and the state at time t minus 1. So for example, where our motion model was small motion, this probability was large close to the particle position and small far away from it. And finally, we have our sensing model, which says if we have an observation, which is z of t, so we've gotten this observation, a new frame of the video in at time t, how likely is the state x of t given this measurement? Sorry, I got that backwards. How likely is the measurement we just got if the true state of the system is x of t? And this is sort of a standard Bayesian framework for thinking about beliefs, where we're incorporating what we know to update our belief based on our prior belief. I think there's one caution I need to make here, which is sometimes we encode our belief in the weights of our particles, and sometimes we encode our belief in the distribution of those particles. A particle filter encodes the belief function as a weighted distribution of particles. And so you don't necessarily see all the terms of this equation as multiplicative factors. Sometimes you see them as things you do to your particles, which change the distribution, and that distribution is the belief. Two questions came in at a similar time. Three questions. Wow. So one is about being stuck on the Kalman filter with code passing Bonnie. but for the outputted image not approaching the template target. And I'm really not equipped here in this setting to help with debugging, other than to suggest potentially tuning some of the noise or covariance parameters that are available for you to tune, or really going through your code with a fine-tooth comb and checking that its output makes sense given the input you're given. The operation of a Kalman filter shouldn't be a black box. At each step, the matrices have meaning, and you can actually either plot that out or just read through them. That's how I recommend debugging the Kalman filter. The next question I got was, you said you looked at 6 different motion models to find a good one. What considerations am I making in finding a good motion model? Success on the problem set is sort of the glib answer, but more seriously, I was looking for a motion model that stayed tightly clustered on the target prior to an occlusion, or during an occlusion. So it didn't have too much dispersion, and I had enough particles in a good place to recover the target after the occlusion had passed. I was also looking for a motion model that was as simple as possible, because simple is always better than complex. And I was finally looking for a motion model that wasn't overly tuned to the problem set. I don't love the idea of hard coding a motion model that perfectly tracks the object because you've plotted out every point and written down what it is and made your motion model that way. You want your motion model to be general enough that it captures the motion you observe. So if a parameter is clearly changing, be it the X or the Y or the scale, then your motion model needs to allow for changes in those variables. And if a value isn't changing, your motion model should restrict changes in that dimension. Someone in the live chat just said the Kalman question is probably because the image list in experiment.py is not sorted, and someone else has +1 that. Yes, that was an oversight based on different operating systems people use. It's been discussed on Piazza. Could someone post in the live chat which Piazza thread the sorting of images was discussed in? If you're having problems with your Kalman filter, you may need to sort the images coming in by name. And the last question I see is, in my hand tracking example, you showed the window for the template as a square that is different from the initial template size. Are we allowed to alter the template width and height? I think that's a question that needs to be posted on Piazza so everyone can benefit from the answer that all the TAs come to. I don't feel comfortable making that determination myself. I was just trying to throw together an example for these office hours and moving kind of quickly. So I picked a square template that seemed to track all right. Don't take that as indicative of what you should do on your problem set. All right, we have 2 minutes left, which is time for one more question. I see the question, which is, how can the particle filter be mapped to the belief formula? And I'm really wishing that at this moment I had my prior office hour slides so we can pull them up as well. But if we go through sort of one iteration of the particle filter cycle, which I show in my prior office hour slides, we start with some distribution of particles. So all the particles are scattered about the image somewhere. We have belief x of t minus 1 is represented by the distribution of particles going into that loop. Then we're going to move the particles, which is equivalent to multiplying by this sort of motion model term. By moving the particles in accordance with the motion model, in particular, moving them including a random factor that mirrors the probability of reaching the new state, we get a new distribution that includes this contribution from the motion model. And then the measurement step where we calculate weights for the particles and resample is the result of incorporating this sensing model multiplicative factor here. So that's sort of at a high level how the particle filter maps to the belief function. The distribution of your particles going in is your prior belief. You move the particles, including randomness, that matches this probability function. And so that gives you your state now, including the effects of your motion model. And then you weight the particles according to your sensing model and resample, which gives you your belief at time t. And with that, everyone, I think we're done. It's 10 o'clock. Thank you all for coming. The TAs are always available to answer questions on Piazza, and we're happy to discuss computer vision with you whenever you'd like. All right. Good night, everyone.